Okay, I think we can start. So welcome everyone to this EDEM webinar series. Today our expert is Eric.
Perfect. Thanks, Caesar. Appreciate it. And good morning, good afternoon, good evening for wherever you're joining us from today in the world. My name is Eric Feichel, and during this webinar, I plan on going over an application where we will leverage two of Altair's software packages, EDEM for the DEM simulations and MotionSolve for the multi-body dynamics solution. And the unique aspect of this approach, or the challenge that we're addressing here and demonstrating in this webinar, is how can we control the motion of components, the motion of geometry in our DEM simulation based on some feedback of the presence of particles in the simulation. So in the example that I'll go over today, it's a relatively straightforward or simple example where we've got a hopper of material that's being filled with two streams of material. And there's a couple of sensors that we're using to detect the presence of the particles, and then the motor that's driving the inclined auger. Its motion will be a function of the sensor signal. And I also will point out here right now that the information I'm going through is available to everyone that's participating. The information, I mean the models that I'll be showing today came from this Altair Community post. The Altair Community is a great place to access things like this, tutorials that walk you through not only EDEM, but any Altair software. There's training that's linked in, there's YouTube videos that are linked for how to, and in this particular tutorial, you can also access the files. So I've already downloaded the motion control based on geometry force files, the zip file, and unpacked it on my computer. Caesar, did you have another comment before I continue on?
No, nothing else. I just want to confirm that everyone is able to see the screen. I could see one of the attendees go off and then back again. So it's back again. I can see it's online. So we should be able to carry on. And also a couple of people just join as well.
Okay, perfect. So to get to the Altair community, it's simply just the community.altair.com. And if you would search for EDEM MotionSolve force sensor, this would come up. Alternatively, you could search for the entire name, the optimization of bulk handling control system using force, feedback with Altair, EDEM Inspire, and MotionSolve co-simulation. So I've downloaded the files. I'll bring up my directory that I've pulled these into. So this is the zip file that I've already downloaded that you can access from the Altair community. And you'll see in that data set, there's a variety of different folders, a couple of EDEM specific folders, a couple of Inspire. Inspire is Altair's CAD package. And it's CAD package, and also we will leverage Inspire to set up the multi-body dynamics model, and then a couple of motion models. I'll point out that for this application, the software that I was using or am using today is EDEM 2023.0. In fact, 2023.0 for all of the softwares, and including Inspire. It should work on anything newer, but going to older versions earlier than 2023 might present some challenges. So I'm just launching Altair Inspire, and we'll start with the CAD geometry. So I'm going to, once Inspire loads on my computer, we'll open up the CAD package. So file open, and I will open up this stmod file. That's the extension of an Inspire model. And you can see here that we've got the geometry already predefined. we've got the inclined auger, the hoppers, the two inlets, the factories that are buried inside of the inlets up here, and we've got a couple of these force sensors down here. And I'll just make this semi-transparent so we can see what's going on the inside. So those two yellow plates are ultimately going to be what we use as the sensor, what will be passed back and forth to EDEM and MotionSolve. The challenge here, that the limitation with just using EDEM to solve this type of problem is there's no way to set up the motions in EDEM. So you've got the ability to define all kinds of different geometry motions, linear translation, rotation. You can input force controllers for both torque and velocity. You set up conveyor translation motions and things of that nature. But within EDEM, there's no feedback system that you could use directly to say, if there's particles contacting a certain surface, then do this, turn on a motor, or what have you. So that's why we've headed down the path of leveraging the multi-body dynamics co-simulation to attack this or address this challenge. So the first thing that I'll point out in the Inspire model is that oftentimes when I'm setting up an EDEM simulation, for those of you that might be new to using EDEM, oftentimes I have on one screen EDEM, and when I'm preparing the geometry, I've got my CAD on another screen or on the same screen. EDEM is a great software. It's intuitive. It's arguably commercially the best DEM software on the market, but it lacks some features that are common in CAD packages that aid in the setup of the model. So if I'm extracting coordinates from a CAD model, I'll pull that directly from the Inspire model so I can define those points in EDEM. Or if I want to hide geometry or unhide geometry, I can easily do that by selecting a component in Inspire and pressing H again to bring it back. In EDEM, that's not so straightforward. So that's why I normally have Inspire session and an EDEM session running in parallel. We need to get this model into EDEM, and normally the way that I would attack this is I'll take all of the geometry that is stationary, that isn't going to be passed through the coupling, and group that together as one step file. An easy way to generate that in Inspire, once you've got all of the CAD defined, is going into the configuration editor. The shortcut for that is F5. In F5, you can see that this brings up this config editor, and I can easily turn off force sensors, this assembly that's grouped together, which has 4 components in it. And I really want the auger off too, because those force sensors are components that I will want to pass through the coupled MotionSolve EDEM simulation. So by pressing F5 again, you can see I've got the same model, just less the sensors and the auger. I can go up here and File, Save As. I normally use a step file. I'll save over the step file that I've created already as the CAD that I will later import into EDEM. So if I switch over to EDEM now, let's just start with a new deck, and I'm going to come down to geometry, import the geometry. I just created that in the Inspire before. So I'm selecting the step file that I just created. I'm working in base units of millimeters, and generally I would leave everything as default when I'm importing this geometry. And after the geometry is imported, perhaps then I would make some refinements to the mesh resolution. If I switch this over to mesh and crank up the opacity to 1, I would say that that's a reasonable representation of the geometry. It's not too heavy with the number of geometry elements, but it's also a reasonable representation, particularly of this circular cross-section for the auger housing. If you had the mesh set too coarse and you are concerned about predicting things like the auger power, if you have too coarse of triangular mesh, you might have areas where you have a clearance that's much smaller than in the physical system that you're trying to replicate. I've got the physical components in here now, but you would see that if we have particles dropping in, they would fall out of the openings where the sensor is, and of course I don't have the auger on the inside. So to get those geometries, I'll eventually import those through the MotionSolve model, and we'll go back to Inspire, turn those components back on. And back to my earlier comment of Inspire is more than just a CAD package. We can leverage a very intuitive and easy to use multi-body dynamics model directly in Inspire. So I've got the motion tab up here, and generally for setting up the motion models, as you would normally read from left to right, working through the ribbon from left to right would be appropriate. We want to define some grounded bodies so that they're fixed, they're not going to move in space. In this case, I don't want the auger to be grounded. I don't want the force sensor to be grounded. So I've selected both of those and pressed H. I'm going to group select all of these guys. So I'm going to select the ground and then group select, and all of those components have turned red, indicating that they're locked. Those components are not going to move. So disable that. And if you were interested to see what components were grounded, you could click on this little properties icon here, and you can see anything that's checked off is a grounded body. Rigid groups. If I bring back all components, if I bring back all components by pressing A, I bring back the auger. If I select the auger assembly and press I can filter that down to just those two components, the auger shaft and flight. I've left those two components as individual elements. I'm just going to delete these geometries or dimensions. I don't need them. I've left those two independent with the motivation, or perhaps with the intention of perhaps someone would take this and want to optimize what is the best auger flight, what's the best pitch or diameter of that auger flight, and to be able to modify those as parameters. If we leave them separate and do a rigid group, we can still do that. Alternatively, we could go back to the geometry and use a Boolean to merge those components together, to not use the rigid group, but that would then make the optimization of the flight a challenge in the future. So in this case, back to the motion tab, I'm going to create a rigid group, which are those two components. Create that, and then also I turn that off, turn all the components back on, and isolate this. I also want to create a rigid group between the pins and the force sensors. So I'm going to select the rigid group and select those two. I'm going to call that force sensor 2. You don't have to change the name, but for ease of readability, you can update them. And then I'm going to select these two and go force sensor 1, because it's sensor 1 and pin 1, create. So I've got the grounded bodies, rigid groups. We do want to define some joints, and we want to define some joints because within the coupled simulation, we need to have a joint between the component that we want to get the forces from and the rest of these now rigid or grounded bodies. If you select the joints as is, it would look for all potential joints that could be in your model, or it will try to interpret all of the joints that are in your model. For the sake of solving that quickly, we can isolate down the components that we know we want to generate a joint between. And so that's really going to be this force sensor and these rings. things. So I'm just going to hide the hopper, hide that guy, hide the auger. We can get rid of the inlets, hide, get rid of the outlet. I don't know why that, oops. Let me try this a different way. Hiding those guys, hide that guy. We don't need those components either. Or there. So now I've got the rigidly grouped yellow components and the supports that are part of that ring. If I select joints and find, it's going to find the potential of 2 joints here, exactly what I want. And in this case, I'm going to select a cylindrical locked joint. I actually don't want these components to move. I want them to be held fast or remain in the same spot. And if I use the locked version of the joint, then they're not going to move. So I'll accept that by right-clicking and swiping to the left across that check mark. Do the search for the joints one more time. Set to cylindrical and locked. It's blue. You can see that indeed is locked. So now we've got the 2 joints defined that are associated with those sensors. We don't have a coupler or bushing to define, but we do have a motor that we want to define. So I'm going to select the auger housing and hide it, select the motor, and I do want the motor to be defined at the center at the end. So that's my first mouse click. The second mouse click is going to be on the same geometry, which just informs Inspire that the motor will be grounded to the global coordinate system. It's not grounded to another component. Alternatively, you could do your first selection on your auger and then a second selection on some supporting member. I do want a speed-based motor. So 60 RPM, this is going to ramp up from 0 up to this steady state speed. And you can see here that I potentially may need to change the direction of the auger. In this case, I want the auger to convey the material up the incline, not down. So really that from looking from the rear of the auger needs to be rotating in a clockwise direction. So I can change that by clicking this arrow, clicking the plus and minus, or up here in the properties editor, changing the direction. There's a reverse direction. So I want it left in the clockwise direction. Speed, we can leave it at 60 RPM or perhaps 200. This option of using a controller, if you use a controller, you would potentially be able to define the inputs of your PID control system. That's really not necessary in this case. I just want the speed to ramp up to our steady state speed and be held there. I'll maybe just save the model here as is. It's asking if I want to overwrite it. That's okay, or I do want to do that. And I could have done this earlier if I bring all of the components back. I could have done this earlier. I could have went directly to running this analysis to see what would happen, to see how the model would behave. And you could see there that very early in the, oops, I got a little click happy. Let me stop that again. In the analysis, the auger is dropping away, and we don't want that, right? We want the auger to stay fixed in its original axis. So we need to address that issue. We can very easily do that. If we get out of the results of the analysis and go back to the motor, I want to restrain the center line of the auger, and we can leave that as a resolute joint so that we don't have any translation. So now if I run this model again, I expect that the auger axis will stay in the appropriate spot, and that kind of looks like the physical system that I want to simulate, right? We've got an auger that is spinning in the right direction to convey the material up the incline. It is just a fixed speed. It's not based on the sensor feedback yet, but we've got the general motion set up. Also, you can click on from this analysis, click on components and get the responses. So here you can see the torque of the motor is going up to something like 6 Newton millimeters and then dropping down very close to 0. I can right click on that plot and look at power. You can see it maybe peaks up at 80 watts while it's accelerating the motor, but then after it's reaching steady state, it's oscillating very close to 0. I think in the demonstration files, I also added at the opposite end of the auger a torsional damper. So same as before, double click on the end of the component. And in this case, I don't want a torsional spring. I just want the damper. The damper, oh, I'll do this drop down. Just the damper is what I'm after. And I'm adding that because realistically, you're not going to have a auger power that's hovering right around 0 watts during steady state. There's going to be some parasitic losses. So if we add that in and then rerun, bring everything back, run the model again, and even as it's running, we can go in here and look at what is the power output that we're getting. In this case, we're now somewhere up to 400 watts. Maybe that's higher than it should be. Maybe it's not high enough, depending on the application. But you can adjust the damping coefficient in that rotational damper to account for those parasitic losses if you would like. So at this point in the model, we would now take it the step further and export the model into MotionSolve. For those of you that have maybe joined late, if you do have any questions as I'm going through the model, please feel free to add them in the chat and I can address them as they come up or at the end of the presentation. There'll be a time for Q&A, but yeah, please feel free to add your questions in the chat as we go. So Inspire and Inspire Motion, I'm using that because it's a great, easy to use CAD package, and it allows me to very easily define this simple multi-body dynamics model. But I find that an easier workflow than going directly to Motion View and defining your model in Motion View. And Motion View, I would say, is tailored more appropriate for more experienced multi-body dynamic analysts that are more familiar with the nomenclature of how to set up markers and motion constraints. It's not quite as intuitive, in my opinion, as the options for defining the motion in Inspire Motion. But the nice thing is, from Inspire Motion, we can export the model. So I've clicked on the property icon next to the Analyze Motion, and up here is where you could set the duration of your run, whether it's a static or dynamic, the frequency that you want as a output, and so on. What we want to do here is export the MDL file. Now you can export the MDL file just as a file, or you can export the MDL file and open the model in Motion View. So that would be this upper option. You also have the option to adjust the units at this point if you wanted to work in different units than millimeters, newtons, kilograms, and seconds, what I've got the model set up for. So I'm just going to, because I already have Motion View open, I'm just going to export the MDL file. And in this case, let's go to the working directory. I'm going to save that, and we now have the model exported. So if I bring over Motion View is the MotionSolve's pre and post processor. I'm going to open up the model that was just generated. So that was in the working directory. And in the working directory, you can see that I've got the same components again, and it's just a little different interface. What we're going to need to do in here to get this model set up so that it will be coupled with EDEM is define a DEM subsystem and adjust how the motor speed is being controlled. If I expand out this submodel, the generic auger hopper model, you can see that I've got a motor in here, and the motion in here is defined based on the inputs from the Inspire motion model. And it's defined in such a way, apologize, that's a little bit small. I don't know if I can make this bigger if I bring this up. Not really. There's a -1 out front of here to change the direction of rotation, a step 5 function that's time-based. So the input variable that we're using here is time. And we've got the inputs for the behavior. So at 0 seconds, the output would be 0. At 0 plus 0.5 seconds, the output is going to be 20.944 radians per second, the equivalent of 200 RPM. So what that means is, if we're looking at this temporally, the speed of the motor is going to be 0 right off the start, but it's going to not necessarily linearly ramp. There's a bit of a curve, but it's going to ramp between 0 and 5 seconds. And after 5 seconds, it should hold at the 200 RPM or 20.944 radians per second. So again, what we need to change in here is adding in the DEM subsystem and controlling the motion of the motor such that it's a function of the forces on the sensor. How do we do that? It's pretty straightforward. Let's start with the DEM system. In the assembly tab, there is this EDEM, create EDEM subsystem. And in this case, I'm going to select this, and for graphics, select the components that I want to include in the coupling. Double-clicking on that graphic brings up this pop-up window, and the components that I want to include in the coupling are the components that I haven't already brought into EDEM, the auger flight and shaft, and the 2 sensors. Not the sensor pins, I don't care about the pins, I just want the sensors. And those are nested inside here. So I'm just going to do this one at a, whoops. Let's try that again. We need the moving auger. I'm not sure why I am not able to add that. Bear with me. Let me try the force sensor, not pin. Okay. Double click again. Force sensor 1, CAD. We want the shaft and the auger. Flight. Okay, so those 4 bodies are what I want to be included as bodies in the coupled simulation. Those bodies will have forces and speeds passed back and forth between EDEM and MotionSolve. So in the EDEM model, staying on the Creator tab, I'm going to enable the coupling server, and maybe I can do this in such a way that we can split the screen so we can see what's going on between both of them. And I'm going to select this create and transfer subsystem. And you can see that we now have the 4 added components here in our model in EDEM. I'm just going to maximize that so we can see it a little bit better. We now have the auger and auger shaft and auger flight, and we have plugs, geometry in the force sensors. Force sensor 1 and 2, and then of course our auger flight and shaft are inside our component. So we can save this model now, leave it in the working directory. And in the meantime, I can stop that coupling server, and then we need to update the motion model so that the speed of the motor is going to be driven by the forces that EDEM will be passing back based on force sensor 1 and force sensor 2. So to do that, we've got the need to add a couple of additional components that didn't come from the motion model. So in the solver, or we need to generate a solver variable, which is under the model variables, and I've selected the upper level object in the model tree so that the solver variable will be nested up there. And I'm going to create the name here, sensor force. You don't have to change the name. Leave it as default, but just for ease of reading. And when I select that sensor force within the panel, I'm going to change that to an expression. And I am just going to copy and paste this expression in that I've already got. And once I have it in, I will explain what it is and also how we will need to modify it. Again, I apologize if this is a little bit small, but basically what I'm calculating here is the product of the magnitude of the two sensors. So we've got square root function and nested inside square root. This is really meant to be fx squared, fy squared, fz squared for force sensor 1, and then we're multiplying, oops, I shouldn't have that space or new line in there, multiplied by the square root of fx, fy, fz, each squared of force sensor 2. You could put in whatever expression you think is appropriate here for your application. My logic for using this is that if either of the force sensors have 0 force, I want the auger to not rotate. So that's why I'm taking the product of the two force sensors. And the other thing that is not clear at this point is why am I using DEM 0.solverArray2.id string with a comma 13, comma 14, and comma 15. I will have to update those because I actually changed the order of the bodies that I added to the coupling system. So I'm just going to click OK out of here and then go into this DEM system that we've generated already and take a look inside these forces. You can see these forces. We've got force 1, 2, 3, and 4 here. And when I have selected force 1, we have force sensor 1. Force sensor 2 is force 1. Somewhat backwards or not intuitive for this naming, but auto-generated names, I can't do anything about that. Force sensor 1 is associated with force 2 generated in this DEM subsystem. 3 and 4 are the auger and the auger shaft, so I don't really care about or need to use those. Also, there's outputs in here. We've got the output 1, 2, 3, and 4. Each output corresponds to the force. So the components that I care about are the two sensors, so that's 1 and 2. And the outputs that I care about are fx, fy, and fz. So you can see here for the force 1, on the connectivity, that's force sensor 2. I want the array values that are indexed at 1, 2, and 3, and 7, 8, and 9. 1, 2, 3, and 7, 8, and 9. And if we look at the full string here, this is the array value with a regular brackets and then curly brackets. The curly brackets indicate that we're passing a variable. And that variable is this DEM 0 subsystem, the solver array, and we're looking at solver array 2. There's 2 arrays. Solver array 2 is what we're extracting, and then the index 1 is the fx. So that this is how I know what index and what variables to pass into this force sensor. So I need to have index 1, 2, and 3, and 7, 8, and 9 in this sensor. So it was 13, 1, 2. I'm just going to expand this so it's easier to modify. 1, 2, and 3, 7, 8, and 9. And I can evaluate this to make sure that there's no error. That looks okay. So now this sensor force is what we're getting out of or this solver variable is going to calculate the product of the magnitude of the two forces, those forces being the particles force exerted on those sensors. We could just go directly from the solver variable and update the motion of our motor at this point, but it might be useful to also know what is the response of that sensor force. Solver variables created on their own won't be tracked, won't be recorded. You won't be able to look at what the values were after the simulation is run. So that's why I would also recommend that you would want to add in an output variable. And the output variable is on the model, analyze outputs. So again, I'm selecting the upper level, I'm selecting output that is an expression. Hit the play button, and in this case, there's predefined 8 different outputs that you could use. I'm just going to use one, and that output is going to be very simple. Pop this guy open, and within those brackets, get rid of the double brackets, I am just going to pass the variable value of the sensor force, and maybe in this case to show how you could alternatively set up this input. Let me cancel out of this and do this again from scratch. I'll get rid of this 0, and I can come down into the model that exists already and extract the information that I care about. So I've set up the solver variable that is sensor force, and I want that variable value, that VAR, VAL is the input that I'm after. So I can add that in, and in this case, I also need to add in the curly brackets so that it's passed as a variable. I evaluate that, you can see that it's not passing any error, which is appropriate. So by adding this output, you could update the label of that output if you wish. And we can then take a look after the simulation is run, after the coupled simulation is run, of how that coupling was executed, or what that signal on the force was that was used. And then the last thing that we need to do to update this model is change the expression that we're using here to be, instead of based on time, based on the signal sensor value that we're getting. And in this case, I'm just copying and pasting in the model that I've already generated for the sake of time. Again, the -1, changing the orientation or the direction of rotation. I'm pulling from motor 1 in the parameters, the value of the speed. It's passing me an error in the motor because I believe that perhaps the motor is not defined with the same index. So let's come down here to the generic auger hopper model, and we should have motor and data set, parameter, speed, and the value. And it's the 20.94 RPM, so I'm going to add that. Also, I will perhaps have to update this. So that's the sensor, the solver or sensor force. Again, the variable value, putting inside those curly brackets, and add, evaluate. We now no longer have an error. And so the way that this function is working is the speed will be -20.94 RPM multiplied by the step function. The step function is taking in the force sensor signal as the variable, and we've got a 0 indicating that at 0 the speed is going to be 0, and the second 0 indicates that the speed is going to ramp from 0 up to 0 point when the sensor signal force is 0.16. The step function will ramp from 0 to 1, and then beyond sensor signal force of 0.16, this value will return a value of 1. And now that we've got that implemented, our motion is now a function of the forces that we're getting from the signal from the forces. I've got approximately 15 minutes left in the webinar. Normally I would go ahead and run the coupled simulation, but I do want to provide some time for questions. I don't know, Caesar, have you seen any questions that have come in so far?
No, Eric, we don't have any questions so far.
So I'll maybe just loop back to where I started with the presentation. On this Altair Community post, the files that I've went through are on here, the same files that I started with. And then also there is a YouTube video that is generated. It's approximately 42 minutes long, the step-by-step process to walk you through exactly what I've shown here in the webinar. If there aren't any questions, I would maybe just suggest a couple of alternative workflows or things that I would expect our customers would want to do, and perhaps how I would approach those. Back to the CAD model. So perhaps in the CAD model or the Inspire model, maybe in your application, you have a single force sensor, or you want to move the force sensor to another location. You can certainly do that. You can use a single force sensor, 2 or many force sensors. The challenge or trick will just be in a motion view interface when you're setting up the model there, that you need to somehow incorporate that into the variable, the solver variable that was generated. The way that another perhaps stumbling point or something that you need to be aware of is when you're generating this DEM subsystem, when we're going to the assembly and selecting EDEM up here, that's how we generated this. The DEM subsystem is generated kind of as if it's a script, or a script is executed. There's no easy way to, after generating a DEM subsystem, add a component or take a component away. So if I decided I not only wanted the auger flight and shaft to be included, I wanted to make the spout a flexible body, and that needed to be included in the coupled simulation. I can't just take this DEM subsystem and add on to it the spout. I would be forced to, or I would just delete this or deactivate this DEM subsystem and create a brand new EDEM subsystem. And that would involve, again, enabling the coupling server on the EDEM side and selecting the graphics, the bodies that you want to include in the coupling, transfer and create the subsystem. Keep in mind, as you change or as you add more DEM subsystems, the indices of where the force components are, and perhaps depending on the order that you select them, you may need to also adjust in your solver variable what the parameters are that you want to include for the signal. I didn't talk about this, but you should and I mentioned in the video, adjust your communication interval. General rule of thumb is somewhere between a 1-to-1. So this communication interval being equal to the EDEM time step. That would mean that for each EDEM time step, there's a communication loop between MotionSolve and EDEM, where from EDEM it's passing the forces and torques for the particles on the geometry to MotionSolve, and MotionSolve is using that to pass the speed and position of the component back to EDEM. So a 1-to-1 communication interval, perhaps up to 100-to-1. So if your time step is kilohertz, you could get away with 100 hertz or even 0.1 for the communication interval, depending on the dynamics, depending on the specifics of your model. Trying to think of what other nuances or approaches might want to vary. Perhaps you want to use a linear actuator instead of a rotation or motor. To do that, I would go back to the Inspire model. Perhaps isn't logical with this particular geometry, but instead of using a motor, you could just as easily define an actuator that's perhaps pushing material across or screeding material across a bed. You can define the motion of the actuator in much the same way as the motor. Then you have the ability to change the motion constraint, just like you do with the motor, so that the movement is happening only when there's particles present. Any other questions?
Here, we have a question about the copy. If you can comment the time step between EDEM and MotionSolve.
Sure. So I perhaps answered that right after or before I knew that question came in, but
yeah.
Going back to MotionSolve, just to be sure we're all on the same page here, the communication interval, you actually can specify that when you're creating this EDEM subsystem. I just skipped over that. The communication interval by default is set to a kilohertz. But if you've already created the subsystem and you want to modify the communication interval, if you go into the DEM subsystem and select dataset, you can adjust the communication interval here. And again, as a rule of thumb, that communication interval should perhaps at the one end of the spectrum be equal to the EDEM time step. At the other end of the spectrum, perhaps 100 times the EDEM time step. And the EDEM time step is going to be largely driven by the material model, the particle size that you're using to represent the media that you care to simulate. Likely on the order of 1e⁻³ to, maybe that's optimistic, 1e⁻⁴, 1e⁻⁵ would be typical time steps in EDEM.
Yep.
Any other?
Thanks very much. Thanks very much. There are no more questions so far.
Okay, maybe just final recap or to go back to the beginning of the presentation. The Altair Community, if you go to the Altair Community, you've got access to the models that I worked with here, that I downloaded those components. Please note that that was all done in 2023.0. And there is this link to the YouTube videos that have a walkthrough from start to end of how to implement the control of the motion of a component in a DEM simulation by leveraging MotionSolve. There is a plethora of more information on the Altair Community for applications similar to this, but really covering all of Altair's products. If you're looking for information on any of Altair's products, EDEM, MotionSolve, or Inspire, all of those are covered and more on the Altair Community. There's also a user forum that's related to the Altair Community, and there are many videos, an ever-increasing library of how-to videos on YouTube that are a great resource to leverage. Of course, as you're working through these examples, or if you're working through challenges that are specific to EDEM or any Altair product, and you need support, I am part of the global technical team along with Caesar. We're here to help you answer or solve those problems.
Yeah, thank you very much, Eric, for the presentation and the webinar today. Also, for any of you that are new with EDEM, we run trainings roughly every 5 weeks, and the next one is on the 1st of July for any of you that are new with the software. Yeah, well, thank you very much, Eric, and goodbye, everyone.
Bye, everyone.